Hello, everyone, and welcome to our lecture on hypothesis testing. Today, we're going to explore one of the most important concepts in statistics, which is the process of determining whether a claim is supported by evidence or whether it may have simply occurred due to chance. Before we begin discussing the technical aspects, I would like you to reflect on a simple but meaningful question. How do I actually know that something we observed is true? For example, if you notice that your grade improved after studying more, how can you be sure that the improvement is truly caused by your effort and not by easier exams or other external factors? In the same way, when a company claims that a product is effective or when a teacher introduces a new method of instruction, how can we confidently determine whether these claims are valid? These types of questions are exactly what hypothesis testing is designed to answer, as it provides a structure, an objective method for evaluating evidence and making decisions based on data rather than assumptions.
Overview of the lecture. In this lecture, we will carefully and systematically examine the concept of hypothesis testing and breaking it down into several key components that will help you fully understand both the theory and its practical applications. We will begin by defining what hypothesis testing is and what is important in various real life situations, including fields such as business, medicine, and education. After that, we will discuss the two fundamental types of hypothesis, namely the null hypothesis and the alternative hypothesis, and explain how they are formulated. We will then move on to important concepts such as the significance level, the test statistics, and the p-value, all of which play a critical role in the decision-making process. In addition, we will explore the types of errors that can occur in hypothesis testing and understand their implications. To make everything clearer, we will go through the detailed example step by step, allowing you to see how the entire process works in practice. Finally, we will conclude with a summary of the key ideas and emphasize the importance of interpreting results correctly.
Hypothesis definition. Hypothesis testing is a statistical method that allows us to use sample data to evaluate a claim about a population parameter. And it serves as a foundation for making logical and evidence based decisions in situations where uncertainty exists. To better understand this concept, it is helpful to compare it to real life scenario, such as a court trial, where an individual is presumed innocent until proven guilty beyond a reasonable doubt. This presumption of innocence is similar to the null hypothesis in statistics, which represents the default assumption that there is no effect or no difference. Just as a court requires strong evidence before rejecting the assumption of innocence, hypothesis testing requires sufficient statistical evidence before rejecting the null hypothesis. This structured approach ensures that decisions are not made hastily or based on weak observations, but rather on carefully analyzed data. We use this method in almost every field. In medicine, to test if a new drug is more effective than the current treatment. In business, to see if a new marketing strategy actually increases sales. In education, to check if a new teaching method improves student performance. Without this method, we would just be guessing based on observations. Hypothesis testing gives us a structured, objective way to make decisions.
The two hypotheses: null hypothesis, alternative hypothesis, and its definition. The foundation of this process is the two hypotheses we formulate before we even look at our data. These are called the null hypothesis and alternative hypothesis. Let's go through each one. The null hypothesis is a statement of no effect, no difference, or no relationship. It is the default position, the claim that we assumed is true unless we have strong evidence against it. It usually includes an equality sign like equal to, less than or equal to, or greater than or equal to. For example, if you are testing whether the average height of students is 165 centimeter, the null hypothesis would say the average height is equal to 165 centimeter. On the other hand, the alternative hypothesis is a statement that contradicts the null hypothesis. It is what we suspect might be true instead, or what we want to find evidence for. It includes inequalities like not equal to, greater than, or less than. Using the same example, the alternative hypothesis might say the average height is not equal to 165 centimeter.
Deepening understanding of the null hypothesis. The null hypothesis is often misunderstood, so it is important to strengthen our understanding of its role. It is not just a random starting point, it serves as the foundation for objective testing. In hypothesis testing, we assume that the null hypothesis is true at the beginning. This allows us to test whether there is enough evidence to challenge the assumption. Without this starting point, it will be difficult to measure how strong our evidence really is. Another important idea is that the null hypothesis is designed to be neutral. It does not try to prove anything new or exciting. Instead, it represents the idea that nothing has changed or no effect exists. This is important because it prevents bias by starting with a neutral assumption. We avoid jumping to conclusions and ensure that any claim we accept is supported by strong evidence.
Example. Let's look at a quick example to make this clear. Our claim is a factory says their light bulbs last at average of 1200 hours. Our null hypothesis is average lifespan is equal to 1200 hours, and our alternative hypothesis is our average lifespan is not equal to 1200 hours. It is important to write this down before collecting data. If you write them after looking at your data, you might accidentally bias your results. Also, notice that the hypotheses are always about population, not just the sample. We use the sample to make conclusions about the larger group.
Five-step process. Now that we have our hypotheses, how do we actually test them? We follow a standard five-step process. First, state the hypothesis. Second, set the decision criteria. Third, calculate the test statistic. Fourth, find the p-value or critical value. And last but not the least, make a decision and draw a conclusion. Let's break down the terms we use in these steps. Significance level. This is part of our decision criteria. The significance level is the probability that we are willing to take of making the wrong decision. The most common value used is 0.05 or 5%. This means we are comfortable with a 5% chance of concluding there is an effect when there actually isn't one. Sometimes people use 0.01 or 0.10, depending on how high the stakes are. Test statistic. This is a value calculated from our sample data. It measures how far our sample result is from the null hypothesis, depending on the type of data and test we use. This could be a z-score, t-score, or other value. P-value. This is one of the most important concepts in statistics. The p-value is the probability of getting results as extreme as our observed data, assuming that the null hypothesis is true. If the p-value is very small, smaller than our significance level, it means our result is unlikely to happen just by chance. In that case, we say we have enough evidence to reject the null hypothesis. If the p-value is larger than our significance level, we do not have enough evidence to reject it.
Strength of evidence and hypothesis testing. In hypothesis testing, not all evidence is treated equally. Some results provide strong evidence, while others provide weak evidence. The strength of evidence is mainly determined by the p-value. A very small p-value indicates strong evidence against the null hypothesis, while a larger p-value suggests weak evidence. However, it is important to understand that evidence is not simply accept or reject. There is a spectrum. For example, a p-value of 0.049 and 0.051 are very close, yet they lead to different decisions when using an alpha that is equivalent to 0.05. This shows that hypothesis testing involves judgment and interpretation, not just mechanical rules. Understanding the strength of evidence helps us make more thoughtful and responsible conclusions.
Simple diagram for rejection region and non-rejection region. One-tailed versus two-tailed test. We also need to decide what type of test we are running. A two-tailed test is used when the alternative hypothesis says not equal to. We are looking for a difference in either direction, higher or lower. On the other hand, a one-tailed test is used when the alternative says greater than or less than. We are only looking for a difference in one specific direction.
Because we are using sample data, we can never be 100% sure our conclusion is correct. There is always a chance of making an error, and there are two types we need to be aware of. The first one is a type 1 error. This happens when we reject the null hypothesis, but it is actually true. We call this a false positive. In our court analogy, this is convicting an innocent person. The probability of this happen is equal to our significance level. The type 2 error, this happens when we fail to reject the null hypothesis, but it is actually false. This is what we call a false negative. In the court example, this is letting a guilty person go free. We represent this probability as beta sign. We can't eliminate these errors completely, but we can manage them. Usually, lowering the chance of one type of error increases the chance of the other. So we choose our significance level based on which error is more serious in our specific situation.
Role of the significance level. The significance level, often denoted as alpha, plays a crucial role in hypothesis testing because it sets the standard for decision making. It represents the probability of rejecting the null hypothesis when it is actually true. In other words, it defines how much risk we are willing to take in making a wrong decision. A smaller alpha, like 0.01, means we require stronger evidence before rejecting the null hypothesis. This makes the test more strict. A larger alpha, like 0.10, makes it easier to reject the null hypothesis but increases the chance of error. Choosing the right significance level depends on the situation. In a high-risk field like medicine, a smaller alpha is often used to reduce the chance of false conclusion.
Problem statement. Let's put all this together with a concrete example. This will show you exactly how the process works in practice. Scenario. A coffee shop claims that their new cold brew coffee contains an average of 150 milligrams of caffeine per cup. A consumer group believes that the actual amount is different from this. They take a random sample of 25 cups and find that the average caffeine content is 154 milligrams. With a standard deviation of 10 milligrams, we will test this claim using a significance level of 0.05. Step 1. State the hypothesis. Our null hypothesis will be hypothesized mean is equals to 150 milligrams. The alternative hypothesis will be hypothesized mean is not equal to 150 milligrams. And this is a two-tailed test. Step 2. Set the decision criteria. We are using alpha is equal to 0.05. Since this is a two-tailed test, we split the significance level into two parts, 0.025 on each end. Because our sample size is small and we don't know the population standard deviation, we will use a t-test. Step 3. Calculate the test statistic. The formula for the t-statistic is t is equals to sample mean minus hypothesized mean divided by sample standard deviation divided by the square root of sample size. Let's substitute the number. Sample mean is equals to 154 minus the hypothesized mean is equals to 150 divided by the sample standard deviation is equals to 10 divided by the square root of sample size is equals to 25. So our test statistic would be 2. Step 4. Find the p-value. With 24 degrees of freedom and a t-statistic of 2, the p-value is approximately 0.056. Step 5. Make a decision. We compare the p-value to our significance level. P-value is equals to 0.056 and our alpha is equals to 0.05. Since 0.056 is greater than 0.05, we fail to reject the null hypothesis. There is not enough evidence at the 0.05 significance level to support the claim that the average caffeine content is different from 150 milligrams.
Understanding the decision rule. The decision rule is a key part of hypothesis testing because it tells us exactly how to make conclusions based on our calculation. There are two common approaches, using the p-value or using the critical value. Both methods lead to the same conclusion, but they represent the information differently. In the p-value approach, we compare p-value with the significance level. If the p-value is less than or equal to alpha, we reject the null hypothesis. If it is greater, we fail to reject it. This rule provides a clear and consistent way to make decisions, ensuring that different researchers analyzing the same data will reach the same conclusions. Test types and its use cases. You might be wondering, how do I know which test to use? The choice depends on what you're measuring and what information you have. Here are the most common ones. First is the z-test. It is used when you know the population standard deviation and the sample size is large. Usually, n is greater than or equal to 30. Second is the t-test. It is used when you do not know the population standard deviation or the sample size is small. There are also versions to compare two groups, like independent samples, t-test, or paired t-test. Third is a chi-square test. It is used for categorical data to see if there's a relationship between two variables. Lastly, the ANOVA. It is used when you want to compare the means of three or more groups at the same time. Each of these follows the same basic hypothesis testing process we just learned. Only the calculation and the test statistics change.
Assumptions in hypothesis testing. Before performing any hypothesis test, it is important to understand the assumptions that underlie this method. These assumptions are necessary conditions that help ensure the validity and reliability of the results. Without meeting these assumptions, the conclusions drawn from the data might not accurately reflect reality. This is why checking assumptions is considered a critical first step in any statistical analysis. One of the most important assumptions is independence, which means that each observation in the dataset should not influence another. For example, the response of one participant in a study should not affect the response of another. Another common assumption is normality, particularly when dealing with a small sample sizes, where the data should follow a roughly normal distribution. This condition helps ensures that the test statistic behave as expected. There are also another assumption depending on the test being used, such as equal variance when comparing groups. This means that the spread of data across different groups should be similar. If these assumptions is violated, it may affect the accuracy of the results. In some cases, alternative versions of the test can be used when assumptions are not fully met. If assumptions are ignored, the results of the hypothesis test may become misleading. For instance, we might conclude that there is a significance effect when there is none, or fail to detect an effect that actually exists. Therefore, before conducting any hypothesis test, it is always important to verify whether the assumptions are satisfied to ensure trustworthy conclusions.
Limitations of hypothesis testing. While hypothesis testing is a powerful tool, it is not perfect and has certain limitations. One limitation is that results depend heavily on sample data. If the sample is not representative of the population, the conclusions may be misleading. Another limitation is that hypothesis testing focuses on decisions rather than explanations. It tells us whether an effect exists but not why it exists. Because of these limitations, hypothesis testing should always be used alongside critical thinking and proper data collection method. Variability and its effect on results. Variability refers to how spread out the data is, and it plays a major role in hypothesis testing. When variability is high, it becomes harder to detect differences or effects because the data points are more scattered. This can make it difficult to reject the null hypothesis even if a real effect exists. On the other hand, when variability is low, the data is more consistent, making it easier to detect differences and identify significant results. Understanding variability helps explain why similar studies can sometimes produce different conclusions, even when studying the same topic.
Steps in choosing the right test. Choosing the correct statistical test is an essential part of hypothesis testing, since there are different types of tests available. Selecting the wrong one can lead to incorrect or misleading conclusions. This is why it is important to carefully evaluate the situation before deciding which test to use. The first factor to consider is the type of data being analyzed. Data can be numerical, such as measurements and quantities, or categorical, such as labels and groups. The type of data will often determine which statistical methods are appropriate. For example, numerical data is typically analyzed using tests that compare means, while categorical data is analyzed using tests that examine relationships or frequencies. Another factor to consider is the number of groups being compared. If only one group is being compared to a known value, one type of test is used. If two groups are being compared, another test may be more appropriate. When dealing with three or more groups, more advanced methods are required to properly analyze the differences. Lastly, it is important to consider whether certain population parameters, such as the standard deviation, are known or unknown. This can influence whether a z-test or t-test is used. By considering these factors carefully, we can select the most appropriate statistical test and ensure that our results are accurate and meaningful.
Interpreting results correctly. After conducting a hypothesis test, interpreting the results correctly is a crucial step. Many people misunderstand what the results actually mean, which can lead to incorrect conclusions. It is important to remember that hypothesis testing is based on probability and evidence, not absolute certainty. When we reject the null hypothesis, it does not mean that we have proven the alternative hypothesis to be true. Instead, it means that there is enough statistical evidence from the sample to support the alternative hypothesis. This decision is made based on the significance level and the p-value, which indicate how unlikely the observed data is under the null hypothesis. On the other hand, when we fail to reject the null hypothesis, it does not mean that the null hypothesis is true. It means that there is not enough evidence to conclude that it is false. This distinction is very important because it prevents us from making overly confident claims based on limited data. Understanding how to properly interpret results help us avoid common mistakes and ensures that our conclusions are reasonable. It also reminds us that statistical decisions are always made under uncertainty and therefore should be communicated carefully and responsibly.
Why we fail to reject instead of accept? One of the most important principles in hypothesis testing is the phrase fail to reject the null hypothesis. We do not say accept the null hypothesis because we can never prove it is true with absolute certainty. We can only determine whether there is enough evidence against it. When we fail to reject the null hypothesis, it simply means that the data does not prove strong enough evidence to support the alternative hypothesis. This carefully wording helps prevent overconfidence and reminds us that statistical conclusions are always based on limited information.
Strength of evidence and hypothesis testing. In hypothesis testing, not all evidence is treated equally. Some results provide strong evidence, while others provide weak evidence. The strength of evidence is mainly determined by the p-value. A very small p-value indicates strong evidence against the null hypothesis, while a larger p-value suggests weak evidence. However, it is important to understand that evidence is not simply accept or reject. There is a spectrum. For example, a p-value of 0.049 and 0.051 are very close, yet they lead to different decisions when using an alpha that is equivalent to 0.05. This shows that hypothesis testing involves judgment and interpretation, not just mechanical rules. Understanding the strength of evidence helps us make more thoughtful and responsible conclusions.
Practical application. Hypothesis testing is widely used in many real-world situations, making it an essential tool in various fields. It allows researchers, businesses, and professionals to make decisions based on the data rather than assumptions or guesses. This makes it highly valuable in solving real-world problems where evidence-based decisions are needed. In the field of medicine, hypothesis testing is used to determine whether a new drug or treatment is effective. Researchers compare the result of patients who receive the treatment with those who do not and use statistical tests to decide whether the is significant. This helps ensure that medical decisions are based on reliable scientific evidence rather than assumptions. In business, Hypothesis testing is used to evaluate strategies and improve performance. Companies may test whether a new advertisement increases sales, whether a pricing change affects customer behavior, or whether a new product design improves customer satisfaction. By analyzing real data, businesses are able to make informed decisions that reduce risk and improve outcomes. In agribusiness and agriculture, hypothesis testing is specifically important because decisions directly affect the food production, income, and sustainability. Farmers and researchers may test whether a new fertilizer increases crop yield, whether a certain irrigation method improves plant growth, or whether a pest control strategy reduces crop damage. These steps help ensure that farming innovations are truly effective before they are widely adopted. In broader agricultural system, hypothesis testing is also used in studying climate impact, soil management, and livestock productivity. For example, researchers may compare crop performance under different soil treatment or evaluate whether organic farming methods produce significantly different yields from conventional farming. This ensures that agricultural practices are improved based on scientific evidence, helping increase productivity and food security.
Consistency in hypothesis testing. Consistency is an important principle in hypothesis testing. This means that if the same test is repeated under the same condition, it should produce similar results. However, because we're using samples, there will always be some variation in outcomes. This is why repeated studies are often conducted in research.
Common mistakes in hypothesis testing. Despite its importance, hypothesis testing is often misunderstood, and several common mistakes can occur. Being aware of these mistakes helps improve accuracy and ensures better decision making. One of the most common errors is misunderstanding the meaning of the p value. Many people incorrectly believe that the p value represents the probability that the null hypothesis is true. However, the p-value actually measures the probability of observing the data, or something more extreme, assuming that the null hypothesis is true. Misinterpreting this can lead to incorrect conclusions about the results. Another common mistake is choosing the wrong statistical test. Using an inappropriate test for the data can produce misleading results. Additionally, ignoring the assumptions of the test can affect the reliability of the conclusions. These issues highlight the importance of understanding both the method and the data. Lastly, bias can occur when hypotheses are formed after looking at the data. This practice can lead to results that appear significant but are not truly meaningful. To avoid this, hypotheses should always be defined before data analysis. By recognizing and avoiding these mistakes, we can ensure that our hypothesis testing process is accurate and credible.
Summary and takeaways. Let's recap what we have learned. Hypothesis testing is a method to make decisions about populations using sample data. We start with a null hypothesis and only reject if there is strong evidence. Important elements include the significance level, test statistics, and p-value. We can make errors, but we can plan for them by choosing appropriate criteria. We follow a clear step-by-step process to ensure objectivity. Remember that failing to reject the null hypothesis does not mean we have proven it true. It just means that we did not have enough evidence to say it is false. Statistics is about evidence and probability, not absolute proof. I hope this lecture has helped you understand hypothesis testing clearly. If you want to practice more, try writing hypotheses for different scenarios, or work through some practice problems using the steps covered. Thank you for watching.